Reciprocal and quotient relationships. Welcome, everyone. Before we dive into today's new material, let's take a moment to reflect on what we have already covered. In our previous lesson, we focused on defining the 6 fundamental trigonometric ratios: sine, cosine, tangent, cosecant, secant, and cotangent, by looking at the relationships between the sides of a right-angled triangle. Now, as we move into this new topic, it is important to realize that these 6 ratios do not exist in isolation. They are not independent of one another. Instead, they are all deeply interconnected through what we call reciprocal and quotient identities. Over the next few slides, we are going to explore exactly how these ratios relate to each other, which will make solving much more complex trigonometric problems much easier for you. 1. Reciprocal relationships. First, remember that the reciprocal of a fraction, where a is over b, is simply b over a. You're essentially just flipping the fraction upside down. A key property to keep in mind is that if you multiply any number by its reciprocal, the result will always be 1. This is a very useful property when we start simplifying trigonometric identities later on. Applying this to our topic, you'll see that our 6 trigonometric ratios aren't just random, they actually come in specific reciprocal pairs. In the next few slides, we are going to identify exactly which ratios pair up with each other. Now that we've established that we are looking at how the 6 fundamental trigonometric ratios are interconnected, let's start with the basic concept of a reciprocal. Understanding the pairs. Now that we've established the general concept of what a reciprocal is, let's move from abstract fractions to a concrete geometric example. To help us visualize these trigonometric pairs, let's consider a right-angled triangle, labeled ABC. In this triangle, angle B is a right angle, measuring 90 degrees. We will be using angle A as our primary reference angle for all the ratios we are about to discuss. Keep this triangle in mind, as we will use its sides to define the sine, cosecant, cosine, and secant relationships in the next few slides. A sine and cosecant. First, let's recall the definition of the sine of angle A as we know. Sine of A is equal to the length of the opposite side divided by the length of the hypotenuse. Next, we have the cosecant of angle A, which we often abbreviate as CSCA. If you look closely at the fraction, you'll notice something interesting. Cosecant of A is simply the hypotenuse divided by the opposite side. This brings us to the core concept of this slide, the reciprocal relationship. Because the numerator and denominator have essentially swapped places, we can say that cosecant of A is equal to 1 over sine of A. Conversely, you can also express this by saying that sine of A is equal to 1 over cosecant of A. Now that we have our right-angled triangle ABC in front of us, let's look at our first specific pair of reciprocal ratios, sine and cosecant. As we move to the next slide, we will apply this same logic to the next pair, cosine and secant. B cosine and secant. First, let's recall the definition of the cosine of angle A, as we know from our basic ratios. Cosine of angle A is equal to the length of the adjacent side divided by the length of the hypotenuse. Next, we have the secant of angle A, which is the secant of angle A. If you look closely at the fraction, you'll notice something interesting. The secant is simply the flipped version of the cosine. Specifically, secant of angle A is equal to the hypotenuse divided by the adjacent side. Because one is just the upside-down version of the other, we call this a reciprocal relationship. This means we can express it in 2 ways. Either secant of angle A equals 1 over cosine of angle A, or, if you prefer, cosine of angle A equals 1 over secant of angle A. Now that we have looked at the relationship between sine and cosecant, let's move on to our second pair, cosine and secant. Just like the sine and cosecant pair we discussed previously, these two are mathematically tied together. In the next slide, we will apply this same logic to the third pair, tangent and cotangent. See tangent and cotangent. First, let's recall the definition of the tangent of angle A, as we've seen with the other ratios. Tangent of A is equal to the length of the opposite side divided by the length of the adjacent side. Conversely, the cotangent of angle A is simply the flipped version of that ratio. We define cotangent of A as the length of the adjacent side divided by the length of the opposite side. Because these two ratios are just upside-down versions of each other, they share a reciprocal relationship. This means that cotangent of A is equal to 1 divided by tangent of A, or, if you prefer to look at it from the other direction, tangent of A is equal to 1 divided by cotangent of A. Now that we have explored the pairs for sine and cosecant and cosine and secant, let's look at our third and final pair of reciprocal ratios, tangent and cotangent. Keep this pattern in mind, because in the next section, we are going to see how we can use these ratios to derive even more complex relationships using quotients. 2 quotient relationships. Now that we have clearly understood how the trigonometric ratios pair up through reciprocals, let's move on to our second major concept, quotient relationships. While reciprocal identities involve flipping a single fraction, quotient relationships allow us to express one trigonometric ratio as the result of dividing one ratio by another. As you will see in the next few slides, the most significant relationships we focus on involve tangent of angle A and cotangent of angle A, which we are about to derive using the sine and cosine ratios we've already learned. Deriving the tangent quotient. First, let's recall the fundamental definitions we've already learned. We know that the sine of angle A is equal to the opposite side divided by the hypotenuse, and the cosine of angle A is equal to the adjacent side divided by the hypotenuse. To find the quotient relationship, let's perform a simple algebraic operation. Let's divide sine A by cosine A. When we write this out as a fraction, we end up with a complex fraction, where the numerator is the opposite side over the hypotenuse, and the denominator is the adjacent side over the hypotenuse. Now, look at what happens with the algebra. Since both the numerator and the denominator are being divided by the same hypotenuse term, the hypotenuse terms cancel each other out completely. This leaves us with a much simpler fraction, the opposite side divided by the adjacent side. Finally, if we look back at our original definitions from the start of this lesson, we know that the opposite side divided by the adjacent side is exactly how we define the tangent of angle A. Therefore, we have successfully derived that tangent A is equal to sine A divided by cosine A. This is a powerful identity that we will use to find the cotangent in the next slide. Now that we've understood how the trigonometric ratios pair up through reciprocals, let's move on to the second part of our lesson, the quotient relationships. On this slide, we are going to actually derive the formula for tangent from scratch. Deriving the cotangent quotient. Now that we have successfully derived the tangent quotient in the previous slide, let's use that same logic to find the cotangent quotient. Since we know from our reciprocal relationships that cotangent of angle A is simply the reciprocal of tangent of angle A, we can write cotangent of angle A equals 1 over tangent of angle A now, if we substitute the formula we just derived, which is sine of angle A over cosine of angle A, into the denominator, we get 1 over the fraction sine of angle A over cosine of this angle A. To simplify this, remember that dividing by a fraction is the same as multiplying by its reciprocal. When we flip that fraction, the cosine of angle moves to the top, and the sine of angle moves to the bottom. This leaves us with our final, simplified quotient relationship. Cotangent of angle A equals cosine of angle A divided by sine of angle A. This completes our set of fundamental quotient identities. Real-world application example. Now that we have mastered the theoretical definitions of these reciprocal and quotient identities, let's see how we can apply them to a practical, real-world problem. Imagine a technician who is leaning a ladder against a vertical wall. This setup naturally forms a right-angled triangle, where the wall and the ground meet at a 90-degree angle. Let's focus on the angle formed between the ladder and the ground, which we will call angle A for this specific problem, we are given a starting piece of information. The sine of angle A is equal to 4/5. We will use this single value to find all the other trigonometric ratios in the following steps. Step 1. Find \CSC $1 using reciprocal relationship. We know that cosecant of A equals 1 divided by sine of A. Now, let's substitute the value we were given in the previous step, which was sine of A equals 4/5. So, our equation becomes cosecant of A equals 1 divided by the fraction 4/5. When we divide 1 by a fraction, we simply take the reciprocal, which flips the fraction. Therefore, our final result is cosecant of A equals 5/4. Now that we have our scenario from the previous slide, let's move into step 1 of our calculation. We are looking for the cosecant of angle A. To do this, we'll use the reciprocal relationship we discussed earlier in the lesson. Step 2. Find \cos A to help calculate the quotient. Now that we have found the cosecant, we need to find the cosine to help us move toward our final goal of finding the tangent. To do this, let's look back at our given information from the previous slide. We know that the sine of angle A is 4/5, which, as we've discussed, represents the ratio of the opposite side to the hypotenuse. This means our opposite side is 4 and our hypotenuse is 5. To find the length of the adjacent side, we can apply the Pythagorean theorem. By calculating the missing side, we find that the adjacent side must be 3. Now, with all 3 sides identified, calculating the cosine is straightforward. Since cosine is the ratio of the adjacent side to the hypotenuse, we simply take our adjacent side of 3 and divide it by our hypotenuse of 5, giving us a cosine of angle A equal to 3/5. Step 3. Find \tan A using the quotient relationship. As we saw on slide 8, we know that tangent of A is equal to sine of A divided by cosine of A. Now, let's substitute the actual values we've been working with into this formula. We will take our sine value of 4/5 and divide it by our cosine value of 3/5. When you look at this fraction within a fraction, notice that the denominators, which are both 5, cancel each other out. This leaves us with just the numerators, giving us our final result. Tangent of A equals 4/3. Now that we have found the value for cosine in the previous step, let's move on to step 3, where we find the tangent of angle A using the quotient relationship we derived earlier in the lesson. This completes our calculation for the latter scenario, and in the next slide, I'll highlight some common pitfalls to watch out for when working with these identities. Common mistakes to avoid. First, watch out for confusing the reciprocal pairs. It is a very common mistake to accidentally pair sine with secant. To avoid this, I want you to use a simple memory trick. Notice that the S and the C always swap. Sine goes with cosecant, and cosine goes with secant. If you remember that the starting letters switch, you'll always pair them correctly. Second, be very careful with your notation. There is a huge difference between the reciprocal of sine, which is 1/sine of A, and the inverse sine function, written as sine to the power of -1 of A. Remember, cosecant is just a ratio of sides in our triangle, whereas the inverse sine is a tool we use when we are trying to find an unknown angle. Don't mix them up. Finally, keep an eye on your algebra, especially when using the quotient relationships we derived earlier. When you are calculating tangent of A by dividing sine of A by cosine of A, make sure you are dividing the actual numerical values of the ratios themselves. A common error is to accidentally try to divide the angles, which will lead you to a completely incorrect result. Stay focused on the values, and you'll do great. Now, before we wrap up and look at our final summary table, I want to pause and discuss some common pitfalls. Even if you understand the formulas, it is very easy to make small errors that can lead to the wrong answer. Key takeaways. All right, we have reached our final slide, which serves as a comprehensive summary of everything we have covered in this lesson. I highly recommend you take a moment to review this table, as it consolidates all the reciprocal and quotient identities we've derived today into one single reference point. Let's go through it row by row. Starting with the sine of angle A, We know from our earlier discussion on reciprocal pairs that sine of A is equal to 1 over cosecant of A for its quotient relationship. We can also express it as tangent of A multiplied by cosine of A. Moving down to cosine of A, its reciprocal is 1 over secant of A, and just like we saw in our derivation, cosine of A can also be expressed through the quotient relationship of cotangent of A multiplied by sine of A. Next, let's look at tangent of A as we discussed in the context of the tangent and cotangent pair. Tangent of A is the reciprocal of cotangent of A, and, as we proved mathematically in slide 8, the quotient relationship is simply sine of A divided by cosine of A. Now, let's look at the reciprocal functions. For cosecant of A, the reciprocal relationship is 1 over sine of A, and its quotient relationship is also expressed as 1 over sine of A. Similarly, for secant of A, the reciprocal is 1 over cosine of A, and its quotient relationship is also 1 over cosine of A. Finally, for cotangent of A, we have the reciprocal relationship of 1 over tangent of A, and the quotient relationship we derived in slide 9, which is cosine of A divided by sine of A. If you can master this table, you will have all the tools necessary to navigate complex trigonometric problems and simplify them with ease. This concludes our lesson on reciprocal and quotient relationships. Great job today!